Hey, my friend. Tonight, let's slow everything down. This is a quiet journey into the time before stars existed, when the universe was dark, calm, and still learning how to wake up. You don't need to stay focused or understand everything. Just listen, relax, and let the science carry you gently towards sleep. Chapter 1. When the universe was young, but empty. When we talk about time before stars existed, it can sound like we are describing a blank stage, darkness, silence, and nothing happening. But the early universe was not empty in the way an unlit room is empty. It was full of matter and radiation, full of motion and change, and full of rules quietly shaping what would come next. The emptiness was mostly an emptiness of familiar landmarks. There were no suns, no galaxies, no glowing clouds with edges you could trace. The universe was young, and yet it already contained the raw ingredients for everything we see today. Right after the Big Bang, the universe was extremely hot and dense. In those earliest moments, matter and light were tightly coupled, behaving like a single restless fluid. Charged particles and photons collided constantly. Light existed everywhere, but it could not travel freely because the universe was opaque. It is helpful to imagine a bright fog where every photon is scattered again and again. The cosmos was luminous in energy, but it was not a place where you could see across distance. The concept of a view did not really apply because the universe was, for a time, its own barrier to sight. As space expanded, the universe cooled. Cooling did not mean heat escaping outward into an external coldness. There was no outside. Cooling happened because expansion stretches the wavelengths of radiation and lowers the average energy per particle. The same contents were spread through an ever larger volume, and the temperature and density fell as a natural consequence. Over time, the early plasma became less frantic. Protons and neutrons formed, and then, as the universe cooled further, those building blocks began to combine into the simplest atomic nuclei. Light element formation left the cosmos dominated by hydrogen and helium, with only trace amounts of other light nuclei. This matters for a simple reason. Stars do not form from complicated chemistry at first. They begin with what the early universe provides, and the early universe provides mostly hydrogen and helium. Yet having fuel is not the same as having a star. A star is not merely hot gas. A star is a gravitational machine. Gas must gather, compress, heat up, and remain bound long enough for nuclear fusion to sustain itself. In the early universe, matter was distributed with remarkable smoothness on large scales. Gravity could not immediately carve that nearly uniform sea into bright, compact objects. The path to the first starlight began with something much quieter than ignition, the slow growth of tiny differences in density, barely more than subtle ripples in an otherwise even cosmic medium. Before those small differences could grow into anything that glows, another transition had to occur. The universe needed to become transparent. This happened during the epoch astronomers call recombination, when the temperature dropped enough for electrons to bind to atomic nuclei and form neutral atoms. The name can be misleading, as if something is happening again, but it refers to electrons combining with nuclei after a long period of being separated in a plasma. When electrons were mostly free, they scattered light extremely efficiently, keeping the universe opaque. Once they became bound into atoms, that scattering dropped dramatically, and the cosmic fog cleared. For the first time, light could travel freely over great distances. The light present at this moment is still with us. Over cosmic time, it has been stretched by expansion and cooled into what we now observe as the cosmic microwave background, a nearly uniform afterglow that fills the entire sky. It does not come from stars. It comes from the universe itself becoming transparent, allowing the existing radiation field to stream freely through space. This background is also a kind of boundary. It is the earliest light we can directly observe, and it carries the imprint of the small density variations that later grew into the large-scale structure of the cosmos. Now picture the universe just after this clearing. There is still no starlight, no galaxies, no bright points. Yet the cosmos is far from nothing. Space is filled with neutral hydrogen and helium gas. A bath of background radiation glides through it in all directions. Gravity is everywhere. The universe is expanding, but within that expansion, gravity is patiently beginning to gather matter into slightly denser regions. This is the beginning of a long, dim era often called the cosmic dark ages, a period defined not by a lack of physics, but by a lack of luminous objects. Calling it empty is useful only if we are clear about what is missing. What is missing is light produced by concentrated, compact sources. In a modern night sky, darkness is punctuated by stars because stars are localized furnaces. In the pre-stellar universe, energy was not concentrated in that way. The universe had a diffuse glow in the form of background radiation, but no shining islands. There were no sharp outlines, no familiar scales, no constellations. The cosmos was a nearly uniform medium with slight texture, more like a vast, gently changing atmosphere than a landscape of objects. In this stage, time behaves in a way that can feel unfamiliar. The universe is changing constantly, but not with the rapid drama we associate with explosions or collisions. It changes through slow, relentless processes. Expansion lowers temperatures and densities. Gravity amplifies slight differences. Gas responds to pressure and cooling. The future depends on a competition. Gravity tries to pull matter together, while thermal motion and pressure resist collapse. For a gas cloud to become a star, it must lose energy, cool, and compress, moving from diffuse to dense. But at this early stage, there are few efficient pathways for gas to shed its heat. The universe is simple, and that simplicity slows down the march toward the first bright structures. Even so, the direction of the story is already set. The irregularities imprinted in the early universe act like a faint blueprint. Regions that are just a little denser pull in more matter and become denser still, in a gradual feedback loop. Regions that are a little less dense fall behind. Over long spans of time, structure begins to emerge from near uniformity. The cosmic microwave background observed today preserves evidence that those early differences existed, and it is one of the reasons scientists can describe the universe's youth with such confidence. We still see the trace pattern of the seeds that later became galaxies and clusters. There is another kind of quiet significance here. Once neutral atoms exist, the universe becomes a place where chemistry can begin in earnest. The earliest cosmos is chemically simple, but simplicity is powerful. Under the right conditions, hydrogen can form molecules, and molecules can help gas clouds cool by radiating energy away. Cooling is not a detail, it is a doorway. When gas cools, it becomes easier for gravity to compress it, and compression is what eventually brings temperatures and densities high enough for the first stars to ignite. The universe does not leap into starlight. It prepares for it slowly by making collapse possible. If you could somehow exist in this era, the experience would not match any familiar scene. You would not see a black sky peppered with stars. You would not see glowing nebulae. You would be immersed in thin, cooling gas by human standards, and the dominant light around you would be a faint background coming uniformly from every direction. There would be no single source to look toward, because the universe itself would be the source. It would feel less like standing under a sky and more like floating inside a vast, evenly lit fog that is gradually dimming as it stretches. This is also the moment when the universe becomes, for the first time, an environment where light can function as a messenger across distance. Once the fog clears, photons can travel, carrying information. Later, when stars and galaxies form, that freedom of light becomes the basis of astronomy and of cosmic history. But in the pre-stellar universe, the messenger has little to report besides the background itself and the gentle evolution of gas and structure. It is a quiet universe, but it is not a stagnant one. So when we say the universe was young but empty, we are describing a cosmos that had not yet learned to shine. It had matter and it had light, but it had not yet concentrated either into the brilliant engines we call stars. Instead, it was in a formative stage, transparent, cooling, textured with tiny density variations, and slowly preparing the conditions for the first ignition. And there is something calming in that picture. The universe has known long stretches of darkness that were still full of quiet progress, full of slow settling, full of gentle change. If your day has been crowded with brightness and noise, you can let it drift outward the way the early cosmos did, spreading, cooling, and becoming simpler. You do not have to force the next moment. You can let it form naturally and rest inside the calm of a universe that has always known how to become still. Chapter 2. The Last Light Before Darkness. There was a moment in the history of the universe when light was everywhere, yet nowhere in particular. This light did not shine from stars because stars did not exist. It did not come from galaxies or glowing clouds because those structures had not yet formed. Instead, light was woven directly into the fabric of the universe itself, filling all of space as a consequence of its hot and dense beginnings. Chapter 1 described a young universe that had become transparent and empty of familiar objects. This chapter focuses on the quiet transition that made that transparency possible. The last time light and matter were bound together, and the moment they finally parted ways. In the earliest stages after the Big Bang, light could not move freely. Photons, the particles of light, were constantly interacting with charged particles, especially free electrons. Every attempt by a photon to travel any meaningful distance ended almost immediately in a collision. The universe behaved like an opaque plasma, similar in some ways to the interior of a star, where light takes an extraordinarily long time to escape because it is scattered again and again. In this early universe, light existed in enormous quantities, but it could not form beams, shadows, or images. It was trapped in a dense, restless sea of matter. As the universe expanded and cooled, this situation slowly changed. Cooling did not occur because heat flowed away into emptiness. It occurred because expansion diluted energy. Wavelengths of radiation stretched along with space itself, reducing their energy. At the same time, particles lost kinetic energy as the universe grew larger. Eventually, conditions shifted enough that electrons could bind stably to atomic nuclei, forming neutral atoms. This transition marks one of the most important moments in cosmic history because it fundamentally changed how light behaved. Once electrons were bound into atoms, they could no longer scatter photons as efficiently. The universe suddenly became transparent. Photons that had previously been trapped were released almost all at once, free to travel through space without constant interruption. This release was not an explosion or a flash in a localized region. It happened everywhere, across the entire observable universe, because conditions changed everywhere at roughly the same cosmic time. The universe did not light up in the way a lamp turns on. Instead, it stopped blocking its own light. This event is often described as the universe's last moment of widespread illumination before the long darkness of the prestellar era. It is the last light that does not come from stars. From this point onward, light exists primarily as a relic of the past, slowly fading as the universe expands, until new sources of light eventually appear. The radiation released at this moment continues to fill the universe today, stretched and cooled into a faint glow that arrives uniformly from every direction. What makes this light special is not only its origin, but its uniformity. Unlike starlight, which comes from specific locations, this radiation does not point back to a single source. It comes from the entire early universe at once. No matter where an observer looks, they see roughly the same signal because they are looking at the same event from different directions. This uniform glow is one of the strongest pieces of evidence that the universe began in a hot, dense state and evolved through expansion and cooling rather than existing eternally in its current form. Within this light is encoded subtle information about the early universe. Tiny variations in temperature and density appear as slight fluctuations in the radiation. These fluctuations are extremely small, but they are crucial. They reflect the earliest imprints of structure, the faint differences that gravity would later amplify into galaxies, clusters, and the cosmic web. In this sense, the last light before darkness is also the first record of the universe's future. It contains the seeds of everything that will later shine. After this release, the universe entered a new phase. Light no longer interacted strongly with matter. Photons streamed freely, while matter continued evolving under the influence of gravity and cooling. But crucially, matter itself no longer produced significant light. Neutral hydrogen and helium gas do not glow brightly on their own under these conditions. Without stars or other energetic processes, the universe became optically dark, not empty, not inactive, but dark in the specific sense that no new visible light was being generated. This transition reshapes how we should think about darkness. Darkness here is not the absence of energy. The universe is still full of particles, radiation, and motion. Darkness is simply the absence of concentrated, luminous sources. The cosmos becomes like a vast room after the lights have been turned off, where objects are still present, still interacting, but no longer visible to the eye. The difference is that this room is unimaginably large, and the darkness lasts for hundreds of millions of years. During this dark era, the released radiation continues to cool and fade as space expands. Its wavelengths stretch from visible and infrared into the microwave range, and eventually beyond. While it becomes less perceptible, it never disappears. Even today, it permeates all of space as a quiet background, a fossil of the time when the universe last glowed as a whole. Modern instruments can detect it with extraordinary precision, allowing scientists to reconstruct the physical conditions of that early epoch with remarkable confidence. It is important to note what has not yet happened at this stage. There are no stars collapsing, no galaxies rotating, no heavy elements being forged. Those processes belong to a later era. Here, the universe is in a state of suspension. Gravity is working slowly, gathering matter into slightly denser regions, but without light, these changes are invisible. The drama of cosmic structure is unfolding in complete darkness, guided by laws already in place but not yet producing spectacle. This separation between light and matter also marks a conceptual shift. Before this moment, light and matter formed a tightly coupled system, evolving together. Afterward, they become largely independent. Light becomes a messenger that can cross the universe, while matter becomes a sculptor, slowly shaping itself into future sources of light. This division is essential for everything that follows. Without it, the universe would not develop the layered structure of eras that cosmology describes, from dark ages to reionization to the age of galaxies. From a physical standpoint, this moment is one of simplicity emerging from complexity. A turbulent plasma gives way to neutral atoms. Constant interactions give way to long, free paths. Chaos softens into calm. The universe does not stop evolving, but it becomes quieter, more patient. Change continues, but on scales and timescales that feel almost motionless when imagined from a human perspective. If we imagine drifting through space at this time, there would be no night sky as we know it. There would be no points of reference. Light would arrive evenly from all directions, with no shadows and no sense of depth. As time passed, even that uniform glow would dim, not because it was being absorbed, but because the universe itself was stretching it thinner and thinner. Darkness would not rush in. It would settle slowly, like a deepening twilight that never quite ends. This last light before darkness is, in a way, the universe's memory of itself. It is a snapshot taken just before complexity blooms, preserved by expansion and carried forward through time. Long after stars are born and die, long after galaxies collide and disperse, this faint background will still exist, whispering of a time when the universe was young, smooth, and quietly luminous. And there is something deeply reflective in that thought. The universe shines before it knows how to shine again. It lets go of its light, trusting that gravity and time will eventually bring new brightness into being. In the same way, moments of darkness are not endings, but pauses between illuminations. You can allow the light of the day to fade, knowing that even in quiet darkness, the foundations of what comes next are already gently taking shape. Chapter 3: The Beginning of the Cosmic Dark Ages. After the last light of the early universe was released and allowed to travel freely through space, the cosmos entered a phase unlike any other in its history. This was not a sudden collapse into emptiness, nor a dramatic extinguishing of light. Instead, it was a gradual settling into darkness, defined not by destruction, but by absence. The cosmic dark ages began not because something ended violently, but because something had not yet begun. At this stage, the universe had become transparent, and light no longer interacted strongly with matter. Photons streamed away, thinning and cooling as space expanded, while matter was left behind in a quiet, diffuse state. The universe was now filled mostly with neutral hydrogen and helium gas, spread almost uniformly across vast distances. There were no stars to ignite new light, no galaxies to organize matter into luminous systems, and no heavy elements to enrich the cosmic environment. Darkness became the dominant visual condition, not as a void, but as a consequence of simplicity. The term dark ages can be misleading if interpreted through a human lens. In human history, dark ages are often associated with stagnation or loss of knowledge. In cosmology, the cosmic dark ages were anything but stagnant. They were a period of slow, foundational change, governed by well-understood physical laws acting patiently over immense spans of time. Gravity, thermodynamics, and atomic physics were all at work, shaping the future without producing light to announce their progress. During this era, matter existed primarily as neutral gas. Hydrogen atoms, each consisting of a proton and an electron, dominated the cosmic inventory, accompanied by helium atoms formed earlier in the universe's history. These atoms moved through space under the combined influence of cosmic expansion and local gravitational attraction. On the largest scales, expansion continued to pull regions of space away from one another. On smaller scales, gravity began to assert itself, drawing matter into slightly denser regions where the pull was just a little stronger. These density variations were not created during the Dark Ages themselves. They were inherited from earlier times, imprinted as tiny irregularities in the distribution of matter and radiation. At the beginning of the Dark Ages, these differences were still extremely subtle. There were no sharp boundaries, no clouds with edges, no recognizable structures. The universe resembled a nearly uniform fog, with faint variations so gentle that, if translated into a visual image, they would appear almost perfectly smooth. What makes this period remarkable is how much happens without anything being visible. Gravity does not need light to operate. It works silently, accumulating its effects over time. Regions that are slightly denser than average attract more matter, becoming denser still. Regions that are slightly less dense lose matter and become emptier. This slow amplification process is the beginning of cosmic structure formation, even though no structure can yet be seen. At the same time, the thermal state of the universe continued to evolve. As expansion progressed, temperatures dropped further. Gas particles moved more slowly and pressure decreased. Cooling is essential for structure formation because hot gas resists compression. In the Dark Ages, cooling occurred mainly through expansion and through limited atomic processes. The absence of stars meant there were no strong radiation sources to heat the gas back up. The universe, overall, was on a steady path toward lower temperatures and greater calm. One of the most important features of the cosmic Dark Ages is that they marked the longest uninterrupted period without luminous sources in the universe's history. Before this era, the universe glowed as a hot plasma and then as a diffuse background radiation. After this era, stars and galaxies would dominate cosmic light production. But during the Dark Ages, the universe neither glowed uniformly nor shone from localized points. It existed in a visually silent state, where energy flows and physical transformations left no direct optical trace. This darkness was not absolute in a physical sense. Radiation still existed, filling space as a relic from earlier times. However, it steadily redshifted to longer wavelengths, moving out of the range that human eyes or even typical astronomical instruments would associate with visible light. Matter itself remained mostly invisible because neutral hydrogen and helium do not emit strong visible radiation unless energized. Without external energy sources, the universe had no reason to shine. The cosmic Dark Ages are also defined by a kind of separation. Light and matter, once tightly coupled, now followed largely independent paths. Photons traveled freely, carrying information about the early universe outward through expanding space. Matter, meanwhile, began its slow journey toward complexity, guided by gravity and cooling processes. This separation is critical because it allows the universe to develop memory. Light preserves a snapshot of early conditions, while matter evolves into new forms that will later generate new light. From a modern scientific perspective, this era is not directly observable in the same way later epochs are. There are no stars from this time to image, no galaxies to catalog. Instead, knowledge of the Dark Ages comes from theory, from simulations, and from indirect evidence encoded in later structures. The distribution of galaxies today, the properties of the intergalactic medium, and subtle features of background radiation all carry the imprint of processes that occurred during this unseen chapter of cosmic history. The Dark Ages also set strict conditions on what could and could not happen next. The chemical simplicity of the universe limited how efficiently gas could cool. Without heavy elements or dust, cooling relied on a small number of atomic and molecular transitions. This constraint delayed the collapse of gas into dense objects. The universe was ready for stars in principle, but not yet in practice. It needed time to allow gravity to gather matter into regions dense enough to overcome pressure and ignite fusion. In this sense, the Dark Ages represent a period of cosmic patience. The laws of physics did not change, but their consequences unfolded slowly. Nothing was rushed. The universe did not skip steps. It followed a sequence dictated by initial conditions and fundamental interactions. Darkness was not a failure state. It was an intermediate state, required for the transition from a smooth, hot beginning to a structured, luminous cosmos. If one imagines drifting through space during the Dark Ages, the experience would be profoundly disorienting. There would be no stars to orient by, no galaxies to mark distance, no glowing clouds to suggest motion. Space would feel endless and uniform. Any sense of change would come not from sight, but from knowledge of time passing and from the subtle pull of gravity, slowly guiding matter toward future centers of light. This era also highlights an important truth about the universe. Visibility is not a measure of importance. Some of the most consequential processes in cosmic history occur without producing light. The scaffolding of galaxies, the preparation for star formation, and the establishment of large-scale structure all begin in darkness. Light is a latecomer, a byproduct of processes that have already been at work for a long time. Eventually, the Dark Ages would come to an end. Gravity would succeed in forming the first dense objects. The first stars would ignite, flooding their surroundings with radiation and transforming the universe once again. But that transformation belongs to a later chapter. Here, at the beginning of the cosmic Dark Ages, the universe is quiet, neutral, and patient, holding within it the potential for everything that will follow. There is something quietly comforting in this phase of cosmic history. The universe does not hurry toward brightness. It allows darkness to exist as a natural state, a necessary interval between beginnings and awakenings. If you think of your own moments of stillness or quiet as pauses rather than absences, they begin to feel less empty. Like the Dark Ages of the cosmos, they may be times when unseen structures are forming, preparing the way for whatever light comes next. Chapter 4. A universe filled with invisible matter. During the cosmic Dark Ages, the universe was far from empty. Space was permeated by matter everywhere, yet almost none of it could be seen. There were no stars to illuminate it, no glowing nebulae to outline it, and no galaxies to give it form. What existed instead was a vast, nearly uniform sea of invisible material, quietly shaping the future of the cosmos through gravity and motion alone. This chapter explores what that matter was, how it behaved, and why invisibility did not mean insignificance. The dominant form of ordinary matter during this era was simple atomic gas. Hydrogen atoms made up the overwhelming majority, accompanied by helium atoms formed earlier in cosmic history. These atoms were electrically neutral, meaning their electrons were bound to nuclei and no longer free to scatter light efficiently. As a result, the gas did not emit or absorb visible radiation in any strong way. It drifted through space almost silently, interacting mainly through gravity and occasional atomic collisions. This invisibility marks a profound shift from earlier times. When the universe was hotter and ionized, matter and light were tightly coupled, constantly exchanging energy. Now, matter had become largely transparent to the background radiation passing through it. Light streamed on, while atoms remained behind, cooling and clustering in the dark. From this point forward, matter would no longer announce its presence through glow alone. Its influence would be felt indirectly through its gravitational effects. Although the gas was thin by everyday standards, it was spread across enormous volumes. Even a low density, when extended over cosmic distances, represents an immense total mass. Gravity does not care whether matter shines. It responds only to mass and energy. Throughout this era, gravity acted relentlessly, pulling matter toward regions that were just slightly denser than their surroundings. These regions did not yet look like clouds or objects. They were gentle enhancements in an otherwise smooth distribution, detectable only in theory and simulation. In addition to ordinary atomic matter, the universe also contained another, more mysterious component: dark matter. Dark matter does not emit, absorb, or reflect light, making it invisible in an even deeper sense than neutral gas. Its presence is inferred from its gravitational influence on visible matter and on the large-scale structure of the universe. During the Dark Ages, dark matter played a crucial role, acting as an unseen framework around which ordinary matter began to gather. Dark matter behaves differently from atomic gas. It does not interact through electromagnetic forces, so it cannot cool by emitting radiation. Instead, it moves and clusters under gravity alone. Very early in cosmic history, dark matter began forming clumps and filaments, creating a skeletal structure throughout space. Ordinary matter, though initially smoother and more resistant to collapse due to pressure, was gradually drawn into these dark matter wells. In this way, an invisible architecture took shape long before any luminous structure appeared. The interaction between these two forms of matter defines much of the Dark Ages. Atomic gas followed the gravitational contours laid out by dark matter, slowly accumulating in the same regions. But gas also had its own internal pressure and thermal motion, which resisted compression. The balance between gravitational attraction and gas pressure determined how quickly matter could concentrate. Because cooling mechanisms were limited, this process unfolded slowly over vast spans of time. Temperature played a subtle but critical role. As the universe expanded, the gas cooled, reducing pressure and making it easier for gravity to pull atoms together. Cooling was not dramatic or sudden. It was a gradual easing, allowing gas to settle more readily into gravitational wells. In regions where density was slightly higher, cooling proceeded more effectively, further encouraging collapse. This feedback loop began shaping the earliest seeds of structure. even though no stars or galaxies yet existed. Despite this activity, the universe remained visually uniform. There were no sharp contrasts, no bright points to draw the eye. Matter was everywhere, but it lacked definition. The cosmos during this time was less like a landscape and more like a continuous medium, gently flowing and evolving. The absence of light did not indicate inactivity. It indicated that the processes underway operated without producing visible signals. From a modern perspective, studying this era requires indirect methods. Astronomers cannot observe the Dark Ages directly with traditional telescopes because there is no starlight to capture. Instead, they rely on theoretical models, numerical simulations, and later observational signatures that preserve information about early matter distribution. The way galaxies are arranged today, the large-scale web-like structure of the universe, and subtle features in background radiation all carry echoes of how invisible matter behaved during this formative period. The chemical simplicity of the universe also defines this chapter. With only hydrogen and helium available, atomic interactions were limited. There were no heavy elements to facilitate efficient cooling, no dust grains to aid molecular formation. Chemistry existed, but in a minimal form. This simplicity imposed constraints that slowed the pace of change. The universe could not rush toward complexity. It had to wait for gravity to do its work under restricted conditions. Yet simplicity does not mean fragility. Hydrogen, the most abundant element, is remarkably resilient and versatile. Under the right conditions, it can form molecules that assist cooling by allowing gas to radiate energy away more effectively. Even during the Dark Ages, the earliest molecular formations began appearing in tiny amounts within denser regions. Though rare, these molecules subtly altered the thermal behavior of gas, enabling it to lose energy more efficiently and sink deeper into gravitational wells. These microscopic chemical processes, invisible on cosmic scales, played an essential role in shaping what would come next. The invisibility of matter during this era also invites a broader reflection on how the universe operates across all epochs. Much of cosmic evolution depends on components that cannot be seen directly. Dark matter dominates the mass content of the universe, yet remains undetected except through its gravitational pull. Ordinary matter itself can exist in forms that emit little or no light for vast periods of time. Visibility, it turns out, is not a reliable guide to importance. The universe is shaped primarily by what persists and interacts, not by what glows. As time passed, the invisible matter of the Dark Ages grew increasingly structured. Regions of higher density became more pronounced, though still far from the compact objects associated with stars. Gas slowly settled into the gravitational wells created by dark matter, forming extended clouds that spanned enormous regions of space. These clouds were the ancestors of galaxies, though at this stage they lacked any clear boundaries or internal light sources. The universe was quietly organizing itself on scales far larger than anything that would later shine. It is also during this era that the universe's large-scale pattern became firmly established. Filaments, sheets, and vast empty regions began to emerge from the interplay of gravity and expansion. Even though these structures were invisible, their influence was profound. They determined where matter would eventually collapse, where stars would ignite, and where galaxies would form. The familiar cosmic web seen today traces its roots directly to this dark and silent time. If one could somehow observe the Dark Ages with senses beyond sight, The universe would feel dynamic rather than still. Matter would be flowing gently along gravitational gradients. Vast regions would be slowly thickening, while others would become emptier. The pace would be slow, but the direction would be clear. The universe was moving from uniformity toward structure, from simplicity toward complexity, guided entirely by invisible forces acting on invisible matter. In the cosmic dark ages, invisibility was not emptiness, and darkness was not absence. The universe was full, active, and evolving, even if nothing yet shone. It reminds us that progress does not always announce itself, and that some of the most important transformations happen quietly, beyond the reach of light. There is a quiet comfort in this realization. Much like the invisible matter of the early universe, your own unseen thoughts and slow internal changes may be shaping something meaningful, even when nothing outward appears to be happening. Darkness does not mean nothing is there. It can mean that something fundamental is gently taking form, waiting for the right moment to shine. Chapter 5. Gravity at Work Without Light. During the cosmic dark ages, gravity became the quiet architect of the universe. There were no stars to announce its work, no glowing gas to reveal its influence, and no visible motion to mark the passage of change. Yet gravity was everywhere, acting continuously on all matter, shaping the future structure of the cosmos long before the first light appeared. This chapter explores how gravity operated in complete darkness, patiently organizing matter into the foundations of everything that would later shine. Gravity is unique among the fundamental forces in that it never turns off and never repels. Every particle of matter attracts every other, however faintly, and over cosmic distances, even a weak attraction can accumulate enormous effects. In the early universe, gravity had already been at work from the very beginning, but during the Dark Ages it entered a new phase. Matter had become neutral and transparent, radiation had largely decoupled, and the universe had cooled enough for gravitational attraction to begin overcoming the gentle resistance of thermal motion. At the start of this era, matter was distributed almost evenly across space. The differences in density were extremely small, inherited from tiny fluctuations imprinted in the early universe. These variations were not dramatic clumps or clouds, but slight enhancements and deficits in an otherwise smooth cosmic medium. Gravity responded to these differences immediately. Regions with slightly more matter exerted slightly stronger gravitational pull, drawing in surrounding material at a marginally higher rate than less dense regions. This process is subtle but relentless. As matter flowed inward, the density of these regions increased further, strengthening their gravitational influence and allowing them to attract even more matter. Meanwhile, regions with slightly lower density lost material and became emptier. Over long spans of time, this feedback process amplified the original differences, slowly transforming near uniformity into the beginnings of structure. Importantly, all of this happened without producing light. Gravity does not glow when it works. Ordinary atomic gas resisted collapse through pressure. Even cold gas has internal motion as atoms move and collide. This motion generates pressure that counteracts gravitational compression. For gravity to dominate, the pull inward must exceed the outward pressure caused by thermal motion. In the Dark Ages, the universe was cooling steadily as it expanded, reducing this resistance. Cooling did not cause collapse directly, but it made collapse possible by weakening the opposing force. The balance between gravity and pressure determined the pace of cosmic evolution. Where gas was slightly denser and slightly cooler, gravity gained an advantage. Where gas was more diffuse or warmer, collapse was delayed. This created a universe that evolved unevenly, with some regions beginning to organize earlier than others, even though all remained dark to any observer relying on visible light. Dark matter played a crucial supporting role in this gravitational drama. Unlike ordinary matter, dark matter did not experience pressure in the same way because it does not interact through electromagnetic forces. It responded only to gravity. As a result, dark matter began collapsing into clumps and filaments more readily than atomic gas. These structures formed an invisible gravitational landscape, shaping how ordinary matter moved through space. Gas did not fall straight into these dark matter structures all at once. Instead, it responded gradually, drifting along gravitational gradients and settling into the same regions over time. This slow infall allowed gas to compress gently, avoiding violent shocks or rapid heating. The universe favored patience. Structure emerged not through explosions or sudden collapse, but through prolonged accumulation guided by gravity's steady pull. What makes this period especially striking is the absence of visual cues. In later epochs, gravitational processes are accompanied by spectacular displays, glowing disks, energetic outflows, and brilliant stars. During the Dark Ages, gravity worked in silence. There were no photons being emitted to mark where matter was gathering. The universe could only be understood through its future consequences, not through immediate observation. From a modern scientific standpoint, the behavior of gravity during this era is well described by established physical laws. The equations governing gravitational collapse, gas dynamics, and cosmic expansion allow researchers to model the Dark Ages with considerable accuracy. Large numerical simulations show how tiny initial differences evolve into filamentary structures and dense nodes, matching the observed distribution of galaxies in the later universe. These simulations confirm that gravity alone, acting on invisible matter over long periods, is sufficient to explain the large-scale structure we see today. Another important aspect of gravity's role during this time is its influence on time itself. In regions where matter accumulated, gravitational fields grew stronger, subtly affecting the flow of time relative to emptier regions. While these effects were small, they reflected deeper truth of modern physics. Gravity is not just a force acting within space, but a feature of space-time itself. Even in the Dark Ages, space-time was being gently curved by accumulating matter, shaping the pathways along which future light would travel. The slow pace of gravitational collapse also ensured that the universe avoided premature star formation. Gas needed time to cool, compress, and settle into stable configurations before ignition could occur. Gravity provided the gathering force, but it did not rush the process. This delay was essential. If stars had formed too early, the universe would have evolved very differently, with radiation and heavy elements altering subsequent structure formation. The Dark Ages allowed gravity to prepare the stage carefully before introducing new sources of energy. It is worth emphasizing that gravity does not require complexity to operate. It worked just as effectively in a universe composed almost entirely of hydrogen and helium as it does today in a cosmos filled with planets, stars, and galaxies. Its simplicity is part of its power. Given enough time, even the smallest imbalance will grow. The Dark Ages are a testament to the idea that time itself can be a creative force when paired with consistent physical laws. As structures slowly emerged, they did so on scales far larger than individual stars. The first gravitationally bound regions spanned vast volumes containing enormous amounts of gas and dark matter. These regions were the precursors to galaxies and clusters, though at this stage they lacked any sharp boundaries. Gravity was organizing matter hierarchically, building large frameworks first and leaving finer details for later epochs. Throughout all of this, the universe remained visually dark. There were no markers of progress, no flashes to indicate success or failure. Gravity did not need recognition to continue its work. It shaped the universe with unwavering consistency, indifferent to whether its efforts could be seen. Only much later would its results become visible, when compressed gas finally ignited and transformed gravitational potential into radiant energy. In this sense, the Dark Ages challenge a common intuition about action and visibility. They show that profound change does not require spectacle. The universe's most important structures were assembled quietly, without light, guided by forces acting over immense stretches of time. The brilliance of the later cosmos is built upon this long, unseen labor. As the Dark Ages progressed, gravity brought matter ever closer to the conditions needed for the first stars. Gas grew denser, cooling more efficiently in certain regions, sinking deeper into gravitational wells. The universe was approaching a threshold, though it had not yet crossed it. Everything necessary for light was being prepared in darkness. There is something deeply reflective in this phase of cosmic history. Gravity works without urgency, without awareness, and without light, yet it builds the framework for everything luminous and complex that follows. It suggests that not all meaningful work announces itself, and not all progress is visible in the moment. As you let your thoughts settle, it can be comforting to remember that the universe itself spent a long time becoming what it would one day be, guided by quiet forces acting in darkness. Even when nothing seems to be shining, gravity is still at work, drawing things together, shaping futures that have not yet revealed their light. Chapter 6. The first differences that changed everything. In the vast darkness of the early universe, everything might appear uniform at first glance. Space was filled with the same simple ingredients almost everywhere: neutral hydrogen, helium, and dark matter, all drifting through an expanding cosmos. There were no stars, no galaxies, no visible landmarks to suggest variety or direction. Yet beneath this apparent sameness, the universe carried tiny imperfections. These first differences were almost unimaginably small, but they were decisive. Without them, gravity would have had nothing to amplify, and the universe would have remained smooth, dark, and uneventful in the ways that matter cares about most. These differences did not suddenly appear during the cosmic Dark Ages. They were inherited from earlier phases of cosmic history, when the universe was hot, dense, and filled with radiation. The leading picture in modern cosmology is that the earliest expansion took microscopic variations and stretched them across vast distances. Quantum fluctuations, which are unavoidable in nature, became the seeds of slightly different densities from place to place. The universe did not need to be engineered into complexity. It only needed to avoid perfect uniformity. In physics, perfect symmetry is fragile. Give it the smallest disturbance, and time will magnify the consequences. For a long time after those seeds were planted, ordinary matter and light were tightly linked. Photons scattered off free electrons so frequently that radiation and baryonic matter behaved like a single fluid. In that coupled medium, gravity tried to pull denser regions inward while radiation pressure pushed back. This tug of war produced oscillations. Compress a region slightly and radiation pressure pushes outward. Let it expand and gravity pulls it back. These wave-like motions left a faint but persistent signature in the distribution of matter. The universe, long before stars had rhythms. They were not audible in any literal way, but they were real, and they shaped where matter would later prefer to gather. Eventually, neutral atoms formed. Once electrons were bound into atoms, photons stopped scattering so often and began traveling freely through space. Ordinary matter was released from the strong grip of radiation pressure, and the universe entered the long, dark interval you are exploring in this series. But the density field did not reset. It carried forward a map of small overdensities and underdensities, along with the subtle memory of earlier oscillations. By the beginning of the Dark Ages, those differences were still gentle. Nothing looked like a galaxy. Nothing even looked like a cloud in any familiar sense. And yet the blueprint was there. Gravity does not require large contrasts to act. It responds to every imbalance, no matter how slight, and it does so continuously. In regions where matter was even marginally denser than average, gravity was marginally stronger. That small advantage persisted. Over long stretches of time, it drew in more matter from the surroundings. As matter accumulated, the gravitational pull strengthened and the advantage grew. Regions that began slightly underdense did the opposite. They lost matter relative to the average, becoming emptier and emptier in comparison. This is how an initially subtle pattern can become a deep landscape. Time is the amplifier. Ordinary gas, however, does not collapse like dust. Even cold gas contains motion. Atoms move, collide, and generate pressure, and that pressure resists compression. Whether a patch of gas can fall inward depends on scale and temperature. On sufficiently large scales, gravity can dominate. On smaller scales, pressure can smooth things out and prevent growth. This is one reason the early evolution of structure was selective. Some variations were destined to grow, while others were destined to fade. In the earlier era, when light and matter were coupled, radiation itself was a powerful smoothing agent. It could blur the smallest features simply through relentless interaction. After neutrality, gas pressure continued that smoothing on small scales, ensuring that only certain kinds of differences survived long enough to matter. Dark matter made the amplification of differences far more efficient. Because it does not interact with light and does not feel pressure in the electromagnetic sense, it responds to gravity with fewer obstacles. Dark matter began collecting into denser regions earlier and more decisively than the gas. This does not mean dark matter formed solid objects. It formed halos and filaments, extended concentrations that deepened gravitational wells. Those wells became the invisible landscape that guided ordinary matter. Even when the baryonic gas was still reluctant to clump, the dark matter was already shaping the terrain, carving out valleys where gas would later flow. As dark matter concentrations grew, they shaped routes through space. Matter began organizing into extended structures that would later be recognized as the cosmic web. Filaments formed where flows converged, and dense nodes formed where filaments intersected. Between them, large voids developed as matter drained away. During the Dark Ages, this web was not luminous, but it was real. It was the skeleton of the future universe, built in darkness, with gas slowly settling into the hollows that dark matter had already deepened. If you could have mapped gravity then, you would have seen structure long before you could ever see light. The expansion of space never stopped during this process, and that mattered. Expansion worked to dilute matter everywhere, while gravity worked to concentrate matter in particular places. Whether a region grew depended on which effect won locally. In slightly overdense regions, gravity could gradually overcome the tendency of expansion to pull material apart, and the region could begin to behave as a bound system. In slightly underdense regions, expansion won more easily, and matter became more diffuse. This is a quiet but profound competition, a global stretching against local gathering, happening everywhere at once. Because the early differences were small, their growth began in what physicists call a linear regime. In that regime, the pattern stays similar while the contrast increases. Peaks become higher relative to the average, and valleys become deeper, but the overall shape of the landscape remains recognizable. Only later, when peaks become dramatically denser than their surroundings, does evolution become strongly nonlinear. Then mergers, shocks, and heating can reshape the pattern in more complex ways. In the Dark Ages, for much of the universe, growth remained gentle and orderly. The future was being arranged with quiet precision. These differences are also described statistically, because no observer can point to a single unique template that repeats. The distribution is close to Gaussian. Most regions are near average, and truly extreme peaks are rare. That rarity is crucial. Rare peaks, just slightly higher than typical, became the first places where the universe changed qualitatively. They reached the conditions for faster collapse earlier. They drew in gas earlier. They became the first environments where cooling could proceed far enough to allow the formation of dense clouds that would someday ignite. Most of the universe remained close to average for a long time, and that is part of why the Dark Ages are called dark. The first lights were not inevitable everywhere at once. They were concentrated where the earliest differences were just a little stronger than usual. There is another subtlety that shaped these first differences. The gas did not always move exactly with the dark matter. After the universe became neutral, baryonic matter could have residual relative motions with respect to dark matter, inherited from the earlier acoustic era. In some regions, that relative drift made it harder for gas to settle into the smallest gravitational wells. It acted like a gentle wind, reducing early gas accumulation in certain places and delaying the onset of dense clouds. Even small relative motions can matter when everything is delicate, when the universe is still deciding which seeds will grow and which will not. The chemical simplicity of the Dark Ages also made the first differences matter more. With only hydrogen and helium, the gas had fewer ways to radiate away heat. Efficient cooling is what allows gas to compress and deepen density contrasts on small scales. In the absence of heavier elements and dust, the earliest cooling relied on limited pathways, including the formation of small amounts of molecular hydrogen. That meant that regions with slightly higher density, slightly lower temperature, or slightly better conditions for molecule formation had an advantage. Cooling is a kind of permission slip for collapse. If gas cannot cool, it resists compression. If it can cool even a little, gravity can tighten its grip. So the earliest differences were not only about how much matter was present, they were also about how easily that matter could lose energy and become denser. There is a deeper significance here. These early variations show that complexity does not need a complicated starting point. The universe began with simple ingredients and simple rules, but it was not perfectly uniform. That one fact allowed gravity to create hierarchy, smaller concentrations that feed larger ones, filaments that feed nodes, and eventually galaxies that gather into clusters. In a sense, the first differences were the universe's way of breaking symmetry so that history could have direction. A perfectly smooth universe would be timeless in a practical sense. It would expand, yes, but it would not build. It would not develop landmarks. It would not create places. There is also a subtle connection to the arrow of time. The early universe was extraordinarily smooth on large scales, an unusually ordered state. As structure forms, the cosmos becomes more intricate. Gradients sharpen, material falls inward, energy is converted into motion and heat, and new pathways open for entropy to increase. Gravitational clumping can look like the creation of order, but when the full accounting is done, structure formation enables the universe to explore more microstates, not fewer. It creates new kinds of environments and new ways for energy to be redistributed. The first differences, tiny as they were, helped the universe begin that journey from smoothness toward complexity. So the central point is not merely that small differences existed, but that they were enough. The universe did not require large initial lumps, only tiny departures from sameness, and enough time for those departures to matter. Small deviations, patiently amplified, became the architects of everything we see. The first differences did not guarantee any specific galaxy or star, but they made a universe of variety possible at all, and they ensured that darkness could someday be punctuated by light. If you let that settle in, it changes how you might imagine beginnings. The universe did not start with bright landmarks or dramatic structure. It started with near sameness and faint imperfections. And those imperfections, almost too small to notice, became destiny over long spans of time. In the same way, not every meaningful change in a life arrives as a sudden turning point. Some begin as a quiet shift that only becomes clear later. Tonight, you can let the day soften and fade, and allow your thoughts to become simple again, knowing that gentle forces can still carry you somewhere calmer. Chapter 7: The Cooling Universe and the Chemistry of Darkness. As the cosmic dark ages unfolded, one of the most important transformations in the universe was neither dramatic nor visible. It was cooling. Not the cooling of a surface exposed to cold surroundings, but the gradual loss of energy that comes from expansion itself. Space was stretching, and as it stretched, everything within it was changing. Temperatures fell, motion slowed, and matter began to behave differently. This slow cooling, paired with the simplest chemistry imaginable, quietly prepared the universe for its next great transition. Cooling in the early universe was an inevitable consequence of expansion. As space expanded, radiation wavelengths stretched and particles lost kinetic energy. There was no external environment into which heat escaped. Instead, energy was diluted as the same contents occupied a larger and larger volume. This process had already been at work since the universe's earliest moments, but during the Dark Ages, it became especially important because cooling began to affect how matter responded to gravity. At the beginning of this era, ordinary matter existed primarily as neutral atomic gas. dominated by hydrogen with a substantial fraction of helium. These atoms moved freely through space, colliding occasionally, exchanging energy, and responding to gravitational attraction. Even though the gas was extremely thin by everyday standards, temperature still mattered. Thermal motion generated pressure, and pressure resisted gravitational collapse. For gravity to gather matter into dense regions, that pressure needed to weaken. Cooling provided the pathway. As the universe cooled, atomic motion slowed. Collisions became less energetic. Pressure dropped. This did not cause gas to collapse immediately, but it shifted the balance. Regions that were already slightly denser, shaped by the gravitational landscape described in earlier chapters, became increasingly susceptible to compression. Cooling did not determine where structures would form, but it determined whether they could form at all. Cooling alone, however, was not enough. For gas to collapse efficiently, it needed ways to lose energy beyond simple expansion. When gas falls inward under gravity, it heats up. If that heat cannot be removed, pressure builds and collapse stalls. In later cosmic eras, heavy elements and dust provide many efficient cooling channels. During the Dark Ages, the universe had none of those conveniences. Chemistry was limited to the lightest elements, and yet even within those constraints, important processes emerged. The simplest and most abundant atom, hydrogen, played a central role. Neutral hydrogen could interact through collisions and could emit radiation under certain conditions, but those processes were relatively inefficient at the low densities of the Dark Ages. Helium contributed even less to cooling. As a result, large regions of gas remained warm enough to resist rapid collapse for a long time. This delay is one reason the Dark Ages lasted as long as they did. The universe needed patience because its chemistry offered few shortcuts. Despite this simplicity, chemistry did not stand still. Even in a universe composed almost entirely of hydrogen and helium, molecules could form in small amounts. The most important of these was molecular hydrogen. Forming such molecules was difficult because there were no dust grains to catalyze reactions, as there are in later galaxies. Instead, molecular hydrogen formed through a sequence of gas phase reactions involving ions and free electrons left over from earlier times. Though rare, molecular hydrogen had an outsized impact. It provided a new way for gas to radiate energy away. Molecules can rotate and vibrate, and transitions between these states allow them to emit radiation more efficiently than single atoms under certain conditions. Even tiny amounts of molecular hydrogen could significantly enhance cooling in denser regions. This allowed gas to lose heat more effectively as it fell inward, enabling further compression. This chemistry of darkness was not uniform across the universe. Molecular formation was more effective in regions where density was slightly higher, where collisions were more frequent, and where gravitational compression had already begun. In this way, chemistry amplified existing differences rather than erasing them. Regions already favored by gravity gained an additional advantage. They could cool better. Cooling, in turn, allowed them to become denser, creating a feedback loop that nudged the universe closer to its first luminous objects. Temperature and chemistry were thus deeply intertwined. Cooling enabled chemistry, and chemistry enhanced cooling. But both operated within strict limits. Molecular hydrogen could not cool gas indefinitely. There was a floor beyond which cooling became inefficient again. This imposed a characteristic scale on early collapse, influencing the masses and properties of the first dense clouds. The universe was not free to form structures of any size it wished. Its own physical laws constrained what was possible. Throughout this process, darkness remained complete. None of these chemical reactions produced visible light in any appreciable way. The universe was changing internally, not externally. The chemistry of the Dark Ages did not illuminate space. It prepared matter for illumination later. This distinction is crucial. The absence of light did not imply the absence of transformation. It meant that transformation was happening in a form invisible to future eyes. From the standpoint of modern science, the cooling and chemistry of this era are supported by detailed theoretical models and simulations. By applying known atomic physics to early universe conditions, researchers can trace how temperature evolved and how small amounts of molecular hydrogen formed. These models successfully predict when and where gas could first collapse into dense objects, consistent with later observational evidence of early stars and galaxies. What makes this era especially compelling is how minimal the ingredients were. There were no complex molecules, no carbon chains, no oxygen chemistry. And yet, within this stripped-down environment, the universe managed to take its first steps toward complexity. It demonstrates that complexity does not require abundance. It requires opportunity. Cooling created that opportunity by lowering barriers that had previously kept matter diffuse and unstructured. The gradual nature of cooling also shaped the rhythm of cosmic history. Nothing happened quickly. Gas clouds took immense spans of time to change appreciably. The universe did not rush from darkness to light. It lingered in an intermediate state, allowing gravity, temperature, and chemistry to align. This slow tempo is written into the cosmos itself. The first stars were not late because something went wrong. They were late because the universe was following its own rules. As cooling progressed, the universe became increasingly diverse in its internal conditions. Some regions remained too warm and diffuse to collapse, while others crossed critical thresholds and began concentrating matter more effectively. This uneven progress ensured that the first light sources would appear in isolated pockets rather than everywhere at once. The universe would awaken unevenly, with darkness persisting even as the first stars ignited elsewhere. It is also worth noting that cooling affected not just gas, but the future behavior of light itself. Once stars formed, their radiation would interact with the surrounding medium in ways shaped by the prior thermal and chemical state of the gas. The imprint of the Dark Ages would persist, influencing how the universe responded to its first sources of light. Darkness was not erased. It was transformed. The chemistry of the Dark Ages thus represents a quiet bridge between eras. It connects the smooth, hot beginnings of the universe to the complex, luminous structures that followed. Without effective cooling, and even the simplest molecular chemistry, gravity alone would not have been enough. The universe needed all of these elements to work together, slowly and consistently, to make the next step possible. There is a gentle lesson embedded in this story. The universe did not require brilliance to prepare for brilliance. It required patience, simplicity, and time. Cooling happened gradually. Chemistry proceeded quietly. And yet these understated processes determined everything that came after. As you let this chapter settle, it can be calming to remember that even the universe needed long periods of quiet adjustment before it could shine. Change does not always arrive with light or noise. Sometimes it comes as a slow cooling, a subtle shift, or a quiet rearrangement beneath the surface. And in that darkness, something meaningful is already taking shape, waiting for the moment when it can finally begin to glow. Chapter 8. When darkness was the dominant state. For a long span of cosmic history, darkness was not an interruption, it was the norm. After the universe released its last diffuse glow and before the first stars ignited, darkness became the dominant state of reality. This was not a failure of the universe to produce light, nor a temporary malfunction in its evolution. It was a stable natural condition arising from the physical laws that govern matter, energy, and space itself. To understand this era is to understand that light is not the default outcome of cosmic processes. Darkness is. During this phase, the universe was filled with matter and motion, yet it produced almost no visible radiation. Neutral hydrogen and helium gas occupied vast regions of space, drifting and slowly responding to gravity. Dark matter continued shaping the large-scale structure, carving invisible pathways along which ordinary matter flowed. Radiation from earlier times persisted as a faint background, but it steadily stretched to longer wavelengths as the universe expanded, slipping further from visibility. Nothing in this environment favored brightness. The conditions that generate light had not yet assembled. What makes this era distinct is not merely the absence of stars, but the absence of concentrated energy release. Light is produced when energy is liberated rapidly and locally, as in nuclear fusion or energetic collisions. During the Dark Ages, energy transformations were slow and distributed. Gravity gathered matter gradually, gas cooled incrementally, chemistry progressed in tiny steps. No process existed that could suddenly concentrate energy into a luminous point. The universe was active, but it was not expressive. Darkness dominated because the universe was large, dilute, and patient. Expansion had stretched matter thin enough that collisions were infrequent. Without frequent collisions, there was little opportunity to excite atoms or molecules into emitting light. Even when gas flowed into denser regions under gravity, the densities remained low by everyday standards. Heat generated by compression could usually be redistributed or radiated away in non-visible wavelengths. Light, in the form humans intuitively recognize, was simply not an efficient product of the universe's state. This dominance of darkness also reflects a deeper principle. The universe does not optimize for visibility. Physical laws do not aim to produce stars or observers. They follow consistent rules, and the outcomes depend on conditions. In the Dark Ages, those conditions favored neutrality, cooling, and slow structural growth. Darkness was not something to overcome. It was the logical result of the universe doing exactly what physics allowed at that time. From a thermodynamic perspective, the Dark Ages represent a phase where energy gradients were relatively gentle. Large differences in temperature and density drive energetic processes. During this era, such differences were modest. The universe was cooling overall, but it was doing so smoothly. Without sharp gradients, there was no strong engine to generate light. In this sense, darkness can be seen as a sign of equilibrium developing on large scales, even as smaller scale imbalances slowly grew. Another way to understand this period is to compare it with later cosmic eras. When stars appear, they dominate their surroundings energetically. They pour radiation into space, heat nearby gas, and alter chemical pathways. Darkness recedes locally, though it remains vast between galaxies. During the Dark Ages, nothing played that role. There were no dominant sources imposing order or illumination on their environment. Each region evolved largely according to its own initial conditions and the quiet pull of gravity. It is also important to recognize how long this state persisted. Darkness was not brief. It endured for hundreds of millions of years, far longer than the age of human civilization, longer than many dramatic cosmic events that capture imagination. This longevity reinforces the idea that darkness is not an anomaly. It is a stable outcome when matter is diffuse and energy release is constrained. The universe was comfortable in this state. It had no urgency to move on. During this time, information about the universe's structure existed, but it was hidden. Density variations were growing, filaments were forming, and the earliest gravitationally bound regions were taking shape. Yet none of this could be seen directly. The universe contained a great deal of order that had not yet become visible order. Darkness concealed complexity rather than denying it. The cosmos was structured, but the structure had not yet learned how to glow. Modern science confirms this picture through indirect evidence. The distribution of galaxies observed today traces patterns that must have been established during the Dark Ages. The existence of vast cosmic voids implies long periods during which matter drained away without being replenished by luminous processes. The timing of the first stars, inferred from later ionization signatures, indicates a prolonged interval of darkness rather than a rapid transition. All of this supports the conclusion that darkness was the universe's dominant state for a substantial fraction of its early life. The dominance of darkness also shaped what came next. Because the universe spent so long without light, the first luminous objects emerged into an environment that was cold, neutral, and largely unaltered by radiation. This made their impact profound. When the first stars finally ignited, their light did not merely add brightness. It transformed the state of the surrounding universe, heating gas, breaking atoms apart, and ending the Dark Ages in a gradual but irreversible way. The power of that transition depends on how complete the darkness was before it. Darkness, in this sense, acted as a reset. It allowed the universe to evolve structurally without energetic interference. Gravity could assemble large frameworks without radiation pushing back. Chemistry could proceed in a controlled, minimal fashion. When light finally returned, it encountered a universe that was ready to respond dramatically. The long night made the dawn consequential. There is also a conceptual shift that occurs when darkness is understood as dominant rather than deficient. Light becomes something special, something that requires specific conditions to exist. Darkness becomes the baseline, the natural state of an expanding universe filled with cooling matter. Even today, most of the universe remains dark. Stars and galaxies occupy only a tiny fraction of cosmic volume. The Dark Ages were not an exception. They were an early expression of a rule that still largely holds. This perspective alters how we imagine cosmic history. Instead of seeing darkness as a void between brighter chapters, we can see it as a foundational phase that shaped everything else. The universe learned how to organize itself in the absence of illumination. It learned how to build frameworks quietly, how to allow small differences to grow, and how to wait until conditions were right before releasing energy in concentrated forms. In human terms, darkness often carries negative connotations. It suggests ignorance, loss, or absence. In cosmology, darkness is neutral. It is a physical condition arising from density, temperature, and interaction rates. It does not imply emptiness or inactivity. During the Dark Ages, the universe was full, dynamic, and evolving. It simply did so without producing light. As the Dark Ages progressed, darkness remained dominant even as the universe edged closer to change. Dense regions grew denser. Cooling became more effective in certain pockets. Chemistry quietly enabled further collapse. Yet for a long time, none of this pierced the darkness. The universe did not flicker with false starts or brief illuminations. When light finally emerged, it did so decisively, marking a genuine transition rather than a tentative experiment. Understanding this era helps place our own existence in context. We live in a universe where light is abundant locally, where stars fill the sky and illuminate our nights. But that is not the universe's default condition. It is a localized, temporary state enabled by very specific circumstances. For most of cosmic history and across most of cosmic space, darkness prevails. Light is the exception, not the rule. There is a quiet humility in this realization. The universe does not exist to be seen. It exists to follow its laws. Light appears when those laws permit it, and disappears when they do not. The Dark Ages remind us that meaning and structure do not require visibility. Much of what matters unfolds beyond immediate perception. As you rest with this thought, it may be comforting to remember that even the universe itself spent a long time in darkness without being incomplete. Darkness was not an error to be corrected, but a state to be lived through. In the same way, moments of quiet or obscurity in your own life are not gaps in existence. They are part of the natural rhythm of becoming. You can let the day fade, knowing that darkness can be a place of steady preparation where something meaningful continues to form even when nothing yet shines. Chapter 9. The Long Wait for the First Light. For a very long time after the universe became dark, nothing new appeared in the sky. Matter was moving, gravity was working, chemistry was slowly unfolding, yet no point of light broke the uniform darkness. This long wait for the first light was not a mystery to the universe itself. It was the natural outcome of strict physical conditions that had to be satisfied before light could exist in a concentrated, lasting form. Stars are not easy to make. They require patience, alignment, and time on a cosmic scale. The idea that light was delayed can feel counterintuitive. Gravity had been gathering matter for ages. Gas was cooling. Dense regions were becoming denser. And yet ignition did not happen quickly. The reason lies in the balance of forces involved in star formation. Gravity alone is not enough. It must overcome pressure, angular momentum, and the difficulty of shedding energy. Each of these acted as a brake, slowing the universe's progress toward its first luminous objects. As gas flowed into gravitational wells shaped largely by dark matter, it did not fall straight inward. Even the slightest initial motions were conserved, causing gas to rotate as it collapsed. Rotation generates centrifugal support, resisting further compression. This meant that matter could not simply collapse into a point. It had to redistribute angular momentum, spreading some material outward while allowing other portions to sink inward. This process takes time, especially in an environment with limited ways to dissipate energy. Cooling remained a central constraint. As gas compressed under gravity, it heated up. If that heat could not be removed efficiently, pressure increased and slowed further collapse. During later cosmic eras, metals and dust provide many pathways for cooling, allowing gas to collapse relatively quickly. In the early universe, those tools did not exist. Cooling depended primarily on molecular hydrogen and a small number of atomic transitions. These mechanisms were effective only under certain conditions and at certain densities. As a result, collapse proceeded in stages, pausing whenever pressure caught up with gravity. Another factor that prolonged the wait was scale. The first gravitationally bound regions were enormous compared to individual stars. They contained vast amounts of gas spread over large volumes. Gravity worked first to assemble these large structures, not to form small, dense objects immediately. Only after gas settled into the centers of these regions could smaller-scale collapse begin. The universe built its structures from the outside inward, rather than the other way around. Time itself played a critical role. Physical laws do not enforce speed. They enforce consistency. Given enough time, gravity will concentrate matter, but it does not hurry. The Dark Ages were not a holding pattern. They were an active phase of preparation. Every moment of waiting allowed density contrasts to grow, gas to cool incrementally, and gravitational wells to deepen. The universe was not idle. It was aligning conditions that could not be rushed. The first stars also required a threshold to be crossed. Gas had to reach sufficient density and temperature in its core for nuclear fusion to begin. Fusion is not a gradual glow-up. It is a qualitative change. Below the threshold, nothing happens. Above it, a star is born. Reaching that threshold in the early universe was difficult because the lack of cooling limited how dense gas could become. Only the most favorable regions, the rare peaks in the density distribution, could reach the necessary conditions early on. These rare regions were special not because they were designed to be, but because statistics favored them. In a nearly uniform universe, extreme deviations are uncommon. Most regions hovered close to average conditions and evolved slowly. Only a small fraction began significantly denser than their surroundings. These regions gained a head start, attracting more matter and cooling more efficiently. They were the places where the long wait would finally end first. Even within these favored regions, collapse was not smooth. Gas dynamics introduced complexity. Shocks, turbulence, and fragmentation occurred as matter flowed inward. Some material was compressed, while other portions were flung outward or stalled in orbit. The process resembled a slow negotiation between forces rather than a decisive victory for gravity. Each step toward greater density had to be earned. Radiation from the background universe did not help. By this time, the relic radiation from earlier epochs had cooled to such low energies that it no longer influenced gas dynamics significantly. The universe offered no external assistance. The first stars had to be born almost entirely from local conditions, without help from existing luminous neighbors. They were truly pioneers, forming in isolation within an otherwise dark cosmos. Modern simulations of early star formation showed just how narrow the path to first light was. Small changes in density, temperature, or chemical composition could delay or prevent collapse entirely. The universe did not guarantee stars everywhere. It allowed them only where conditions aligned just right. This explains why the first light did not appear all at once, but rather in scattered locations, separated by immense distances of continued darkness. The long wait also shaped the nature of the first stars themselves. Because cooling was inefficient, the collapsing gas clouds tended to be massive. This favored the formation of stars far larger than most stars seen today. These early stars burned hot and fast, shining intensely but briefly. Their eventual deaths would profoundly alter the universe, enriching it with heavier elements and changing the rules of star formation forever. But before any of that could happen, the universe had to endure the silence. The patience of this era is one of its defining features. The universe did not oscillate between darkness and light. It remained dark consistently, allowing processes to mature fully before transitioning. There were no half-formed stars flickering briefly. When the first light appeared, it marked a true turning point, not a tentative experiment. The wait ensured that the dawn was meaningful. This long delay also ensured that the universe had time to establish its large-scale structure before light began reshaping it. Once stars ignited, their radiation would heat and ionize surrounding gas, altering collapse pathways and suppressing new star formation in some regions while enhancing it in others. By waiting, the universe allowed gravity to lay down a framework that would persist even as radiation began to modify the environment. In hindsight, the long wait for the first light can seem excessive. But from a physical standpoint, it was inevitable. Each delay had a cause rooted in fundamental laws. Pressure resisted gravity, rotation resisted collapse, cooling resisted heating, and statistics limited how many regions could reach extreme conditions early. The universe followed these rules without exception. Darkness during this time was not empty or static. It was a state of anticipation written into physics itself. The universe was building tension, accumulating potential energy in compressed gas and deep gravitational wells. When the first star finally ignited, it released energy that had been stored for an immense span of time. The brilliance of first light was proportional to the patience that preceded it. Understanding this weight also reframes how we think about beginnings. The first light was not an instant consequence of the Big Bang. It was the result of a long chain of conditions, each dependent on what came before. The universe did not hurry to become recognizable. It took its time becoming ready. There is something quietly grounding in this realization. Even the universe itself did not rush toward illumination. It allowed darkness to persist until light could truly endure. In a world that often feels impatient, the cosmos offers a different rhythm. Some things cannot be forced. They arrive only when conditions are right. As you reflect on this long cosmic wait, you can let the day release its urgency. The universe reminds us that silence and delay are not failures. They are part of preparation. Just as the first light waited until it could truly shine, you can rest in the quiet, knowing that not everything needs to happen at once, and that patience is sometimes the most fundamental force of all. Chapter 10. The Universe on the Verge of Awakening. By the end of the cosmic dark ages, the universe had changed profoundly, even though it still appeared dark and silent. Nothing in the sky yet announced the coming transformation, but the conditions that had defined darkness were beginning to loosen their hold. Matter was no longer merely drifting. Gravity had sculpted deep wells. Gas had cooled as far as the laws of early chemistry allowed. Molecular pathways, rare but decisive, were operating in the densest regions. The universe was approaching a threshold, not abruptly, but with the slow inevitability that characterizes cosmic change. At this stage, the large-scale structure of the universe was already in place. Filaments of matter stretched across immense distances, intersecting at dense nodes. Vast voids lay between them, emptier than ever before. This structure had formed entirely without light, guided by gravity, acting on small initial differences over long spans of time. The universe had built its framework in darkness. What remained was to activate it. Within the deepest gravitational wells, gas had reached its most advanced state so far. Densities were higher than anywhere else in the cosmos. Temperatures, though still low by stellar standards, were rising locally as gas compressed under its own weight. Cooling processes were working at their limits. Molecular hydrogen, sparse but influential, was allowing gas to radiate away energy just fast enough to continue collapsing. These regions were no longer representative of the universe as a whole. They were exceptions, rare environments where the balance of forces had tipped decisively toward further compression. The universe was not awakening everywhere at once. Most regions remained diffuse, cold, and dark. The verge of awakening applied only to the most favorable locations, the statistical extremes that had been gathering matter and cooling efficiently for a long time. This unevenness is essential. The universe does not transform uniformly. It changes through localized breakthroughs that later influence their surroundings. As collapse continued in these privileged regions, gas clouds began to fragment. Gravity pulled inward, but not all material followed the same path. Small perturbations within collapsing clouds grew, breaking them into substructures. Some fragments gained mass and density faster than others. This internal differentiation marked the final prelude to star formation. The universe was no longer preparing in a general sense. It was preparing specific objects. The physics governing this phase was subtle and unforgiving. Gas needed to shed energy continuously to keep collapsing. Any interruption in cooling could halt progress. Angular momentum had to be redistributed, allowing some material to move outward so that other material could sink deeper inward. Turbulence within the gas both helped and hindered collapse, creating local density enhancements while also injecting motion that resisted compression. The outcome depended on a delicate interplay of all these effects. What makes this moment extraordinary is that nothing fundamentally new was introduced. No new forces appeared. No new particles emerged. The universe was still governed by the same laws that had existed since its earliest moments. What changed was context. Densities crossed thresholds. Cooling became just sufficient. Gravity gained the upper hand locally. Awakening did not require novelty. It required accumulation. From the outside, if such a perspective were possible, the universe would still appear dark. There would be no obvious signal that anything was about to happen. And yet internally, certain regions were approaching conditions where a qualitative transition was unavoidable. Nuclear fusion, the process that defines a star, requires extreme temperature and density in a confined region. The universe was now within reach of those conditions for the first time since its hot beginnings. This is an important distinction. The first stars were not a return to the Big Bang's brightness. They were something entirely different. The early universe glowed because everything was hot and dense everywhere. The coming light would glow because matter had become concentrated in specific places. The universe was transitioning from global brightness to local brilliance. That shift marks one of the most profound changes in cosmic history. The approaching awakening also meant that the Dark Ages were nearly over, even though nothing had yet broken the darkness. The end of an era does not require immediate evidence. It requires conditions that can no longer sustain the old state indefinitely. Once gas clouds reached the point where collapse could proceed faster than all opposing effects combined, light became inevitable. The universe had passed the point of no return. This inevitability, however, did not imply immediacy. Timescales were still vast. Even on the verge of ignition, gas clouds evolved slowly compared to human intuition. But the direction was set. Gravity would continue compressing matter. Temperatures would continue rising locally. Fusion would eventually ignite, not because the universe decided to move on, but because physics left no other stable option. The first stars would dramatically transform their surroundings. Their radiation would ionize nearby gas, breaking atoms apart and heating the environment. Darkness would retreat unevenly, creating expanding bubbles of light within the cosmic web. The universe would enter a new phase, one defined by feedback between light and matter. But at this moment, none of that had happened yet. The universe stood balanced, dark, but pregnant with change. It is worth emphasizing how rare this moment is in cosmic history. There is only one time when the universe stands on the brink of its first light. Later eras would see countless stars ignite and fade, galaxies merge and evolve, and complexity increase dramatically. But the transition from no stars at all to the existence of even one is unique. It marks the point at which the universe begins to generate its own localized energy sources, reshaping everything that follows. From a scientific standpoint, this picture is supported by a convergence of evidence. Observations of the large-scale structure of the universe, studies of early galaxies, and measurements of intergalactic gas all point to a prolonged dark era followed by a gradual, uneven emergence of light. Numerical simulations that incorporate gravity, gas dynamics, and early chemistry reproduce this sequence with remarkable consistency. The universe's awakening is not speculative. It is the logical outcome of well-tested physical principles. Yet there is also something quietly poetic about this moment. The universe did not awaken because it was empty, but because it was full of matter, full of potential energy, full of small differences, amplified patiently over time. Darkness was not a void to be escaped. It was a necessary condition that allowed structures to form undisturbed until they were ready to shine. As the first stars approached ignition, the universe was about to change its relationship with visibility. For the first time, it would produce points of reference, places where light originated, places that could be seen from afar. The cosmos would begin to develop a night sky, even if no one was yet there to witness it. The universe was about to become not just structured, but expressive. And yet, even on the verge of awakening, the universe remained calm. There was no rush, no explosion marking the transition. The laws of physics continued to operate with the same quiet consistency they always had. Awakening, in cosmic terms, is not a sudden jolt. It is a smooth crossing of thresholds that have been approached slowly and carefully. There is something deeply grounding in this final moment of darkness. The universe does not fear the end of an era. It allows change to come naturally when conditions are ready. It reminds us that transformation does not always announce itself loudly. Sometimes it arrives after a long preparation, at the moment when staying the same is no longer possible. As you let this chapter settle, you can imagine the universe holding its breath, not in tension, but in readiness. Darkness has done its work. The framework is built. The energy is gathered. Light is no longer a question of if, but of when. And perhaps there is comfort in that thought. Even the universe itself needed time and silence before it could awaken. If your own day feels heavy or quiet, you do not need to force illumination. Like the cosmos on the verge of its first dawn, you can rest in the knowledge that preparation is already happening, and that when light comes, it will come naturally, without effort, exactly when it is ready to shine. If you're still awake, you're welcome to drift into another video on this channel. There's always more quiet science waiting for you. And if sleep is already close, let the universe keep watch for you tonight. Sweet dreams among the stars.